This is question number 34 in Giancoli textbook chapter 7. The question reads, an internal explosion breaks an object initially at rest into two pieces, one of which has 1.5 times the mass of the other. If 7,500 joules were released in the explosion, how much kinetic energy did each piece acquire? This is a tough question. It just is. I've made a sketch of this random object. I've just made it a blue circle. It could be a bomb or something that explodes and breaks into two fragments, fragments A and B. We can recognize this from the information that's given to us in the problem. The mass of object A, this guy over here on the left, is two times, or I'm sorry, not 2 times, 1.5 times the mass of object B. And so we should start this problem, but at first we should immediately recognize that it's an explosion. And all of these types of problems are addressed via conservation of momentum. So we can say the sum of all of the momentum in the system before this explosion must be equal to the sum of the momentum in the system, all the different parts after the explosion. And if I wanted to, I could say, all right, well, more specifically, that means part A and part B before the explosion. Of course, they're not moving, so therefore the total momentum in the system before the explosion occurs is 0. And by conservation of momentum laws, the sum of all the momentum in the system after the collision ought also to be 0. So right out of the gate, this is 0, this is 0. And so on the left-hand side of this equal sign, I have 0 is equal to MA VA prime plus MB VB prime. And at this point, I'll just kind of draw your attention over here, recognizing that the speed of that particle to the right and of that fragment to the left, even though it's going to be a little bit smaller, their momentum, which is a vector, has to be the same. So whatever that momentum p is going to the right has to be equal in magnitude but opposite in direction to the momentum negative p going to the left. So therefore, p plus negative p is still equal to 0. These two terms, this guy and this guy added together, have to still be 0 if momentum of that system has not changed after the explosion. So if I solve this for the velocity of A prime, so this guy, this is what I want to solve, I'm basically going to subtract this term from both sides. I get negative MB VB prime divided by MA is equal to VA prime. So if A is going to the left, then particle B has to be going in the opposite direction, and that's where this sign comes in. It's a bit awkward since I happen to have chosen A going to the left. So, in this case, I guess technically speaking, I could say, all right, well, this is negative and this guy is positive. But that's the point is that they're simply going in opposite directions, and you should see that negative sign in front of that term kind of helping you out there. So if we put some numbers to this now, and we say, all right, well, then the mass of object B is 1.5 times the mass of object A. Oops, what I meant to say is that the mass of A is 1.5 times the mass of B. So now I'm ready to do some substitutions in this expression, and I can substitute the mass of A with 1.5 times the mass of B down here in the denominator. And here in the numerator, I get negative MB VB prime. And so what happens now is that mass of B cancels out, and I'm left with negative VB over 1.5 is equal to VA prime. And another way of writing that is 1 over 1.5, or I can say negative 2/3 VB. That would be another way of writing the same thing. That should be negative here. Okay, so now that I've written this, actually the real fun begins. So let's take a look at this explosion. We have this explosion in which 7,500 joules of energy are basically now added to the two parts. So I have 7,500 joules given to these two fragments. One fragment goes this way, the other fragment goes that way. So I can say that the energy that's added, this 7,500 joules, is going to be equal to the kinetic energy of particle A after the collision plus the kinetic energy of particle B after the collision. So here's A going to the left over this way, and B is going to the right this way. Remember that kinetic energy is scalar. There's no direction associated with it, unlike momentum. And so then I can write this out, 1/2 the mass of A times the velocity of A squared plus 1/2 mb/vb squared. Of course, these are velocities after the collision. If I wanted to, I could write the prime there to denote that. Now what I'm going to do is substitute some values in for MA and VA. We know that MA is 1.5 times VB. So I'm going to write that here, 1/2 1.5 times the mass of B. I'm doing this because I want to get everything into terms of one of these kinetic energies. There's too many unknowns, so I'm substituting these things in, times VA prime squared. And we also know that VA prime is negative 2/3 the velocity of B. So let me go ahead and do that. I shouldn't have written that here. So let me come back and rewrite this as negative 2/3 the velocity of B, but I'm going to square it. And so we'll see that that negative basically goes away, plus 1/2 mb/vb prime squared. Now, some interesting stuff is going to happen here with these numbers, the 1.5 and the negative 2/3 squared. I'm just going to look at these coefficients here for a second. I'm going to get 1.5, and when I take that negative 2/3 and square it, I'm going to get 4/9. So if I just look at these two numbers, I'm going to get 1.5 times 4, which is going to be equal to 6 over 9, which of course is equal to 2/3. So what really happens here is I'm now going to get 2/3 then times 1/2 mb/vb squared plus 1/2 mb/vb squared. And what happens here now is when I add these two things together, I get 1/2 mvb squared plus 1/2 mv squared, but that's times 2/3. So this is going to become 4/6 mb/vb squared plus 1/2 mb/vb squared, which gives me 5/3. So I basically get 5/3 times this value, 1/2 mb/vb squared. So this is the part here that I think in red is what really makes this problem a very difficult one to solve and work with. So I now have basically 5/3 the kinetic energy of particle B after the collision. This is really what this statement says. And now I can say, well, let's look back at this initial thing description here. I said that the energy added, the 7,500 joules, is equal to kinetic energy A prime plus the kinetic energy B prime. I can say that the kinetic energy of B prime is the energy added. So 5/3 the kinetic energy B prime is equal to the energy added. Let me go ahead and write that out in green. I'm running out of space, so I'm going to write it over here in the corner. I'm saying basically that 5/3 the kinetic energy of B prime is equal to the energy added. This all started here and kind of propagated through this work down this way. So therefore, I can say that the kinetic energy of B after the collision is 3/5 the energy that's been added. So I just simply multiplied both sides by 3/5. That gets rid of the 5/3 over here, and I get 3/5 on the right-hand side. So therefore, the kinetic energy of particle B after the collision is 3/5 times the 7,500 joules which is going to give me 4,500 joules. That's the kinetic energy of particle B, and the kinetic energy of particle A is going to be the balance of that. I'll write that over here on the right-hand side. The kinetic energy of particle A after the collision is going to be the 3,000 joules, because, of course, when we add those two together, they have to be equal to 7,500. Again, this is a tough problem, especially for some of the simultaneous equations that you're dealing with through after some substitutions in this kind of middle area of the problem down here.